Welcome back to our channel. Today we have an exciting topic to discuss: electric cars. They are revolutionizing the way we travel and paving the way towards a more sustainable future. So let's dive right in. Electric cars, also known as electric vehicles, are vehicles powered by electricity stored in rechargeable batteries instead of relying on internal combustion engines that burn fossil fuels. They are becoming increasingly popular due to their environmental benefits and advancements in battery technology. Here is a comprehensive overview of electric cars. The working of electric vehicles comprises of electric motors, battery packs, electric powertrain, regenerative braking, charging systems, and a charging infrastructure to facilitate the charging of the vehicles. Let's start with electric motors. Electric cars are powered by one or more electric motors. These motors use the principle of electromagnetism to convert electrical energy into mechanical energy, which propels the vehicle's electric motors. Start with how electric vehicles work. They encompass an electric motor, which are the key components in electric cars, responsible for converting electrical energy into mechanical energy to propel the vehicle. They operate on the principle of electromagnetism, specifically the interaction between electric current and magnetic fields. The fundamental design of an electric motor consists of several essential components. First is the stator. The stator is the stationary part of the motor and consists of a series of electromagnets. These electromagnets are typically made of copper wire wrapped around a core, which is often laminated to reduce energy loss. When an electric current flows through the wire, it generates a magnetic field. Secondly is the rotor. The rotor is the moving part of the motor and is typically composed of a shaft and a series of permanent magnets or electromagnets. The rotor is positioned inside the stator and is designed to rotate. Third essential component is the commutator, which is also called the inverter. In some types of electric motors, such as brushed direct current motors, a commutator is used to switch the direction of the electric current in the rotor's electromagnet. However, most modern electric cars use brushless motors that utilize electronic inverters to control the flow of current to the electromagnets in the rotor. When an electric current is applied to the motor, it creates a magnetic field in the stator's electromagnet. The magnetic field interacts with the magnets or electromagnets on the rotor, resulting in a force that causes the rotor to rotate. The rotation of the rotor generates mechanical energy, which is transferred to the wheels of the vehicles, propelling it forward. One of the significant advantages of electric motors is their high efficiency. Unlike internal combustion engines found in conventional vehicles, electric motors do not burn fuel and convert it into mechanical energy. Electric motors can deliver nearly instant torque, meaning they can generate maximum power as soon as the driver presses the accelerator pedal. Characteristics of electric motor provides quick acceleration and responsive performance. Additionally, electric motors have fewer moving parts compared to internal combustion engines, resulting in lower maintenance requirements and reduced mechanical complexity. This simplicity contributes to the overall reliability of electric vehicles. In summary, electric motors play a vital role in electric cars by converting electrical energy from the battery into mechanical energy that drives the vehicle. Their higher efficiency, quick acceleration, and reliability makes them an ideal choice for electric vehicle propulsion. Let's move on to the battery pack. The battery pack is a crucial component of electric cars as it stores the electrical energy required to power the electric motor. It is essentially the fuel tank of an electric vehicle. It comprises of, firstly, the battery cells. Battery pack is comprised of multiple individual battery cells that are connected together. These cells are the building blocks of the pack and are responsible for storing and releasing electrical energy. The most common type of battery cell used in electric cars is the lithium-ion battery. Secondly, the lithium-ion battery technology. These batteries are preferred for electric cars due to their high energy density, reliability, and rechargeability. They have a high capacity to store a significant amount of electrical energy relative to their size and weight. The chemistry of lithium-ion batteries involves the movement of lithium ions between the positive and negative electrodes during charging and discharging cycles. That is the battery management system. To ensure the efficiency and safe operation of the battery pack, electric cars are equipped with a battery management system. The battery management system monitors and controls various parameters such as voltage, current, temperature, and state of charge of each individual cell within the pack. It also manages the charging and discharging process to prevent overcharging, overheating, and other potential issues, ensuring the longevity and safety of the battery pack. The energy density and range is a significant factor also. The energy density of the battery pack determines how much electrical energy it can store in relation to its weight and volume. Higher energy density allows for longer driving ranges on a single charge. Advances in lithium-ion battery technology have significantly increased the energy density of electric vehicles' batteries over time, contributing to the development of electric cars' longer ranges. Electric car owners charge their battery packs by connecting their vehicle to a power source. This can be done through various options, such as level 1 charging. This is the slowest form of charging and utilizes a standard household outlet, typically 120 volts. Level 1 charging is convenient for overnight charging, but takes a longer time to fully charge the battery. Level 2 charging. Level 2 chargers require dedicated charging station and use a higher voltage power source, typically 240 volts. They provide faster charging compared to level 1 charging, significantly reducing charging times. Direct current fast charging. These are the fast chargers of electric vehicles. They deliver a higher power direct current to the battery pack, enabling rapid charging. Direct current fast chargers can charge the battery to 80% or more in a relatively short time. The battery lifespan and degradation is also an important factor. Over time, battery cells can experience some level of degradation, leading to a reduction in their capacity to store electrical energy. Factors such as temperature, depth of discharge, and charging and discharging rates can affect the lifespan and degradation of the battery pack. However, manufacturers employ various strategies, such as thermal management systems and active cooling, to mitigate these effects and maximize the lifespan of battery packs. Battery pack is a critical component in electrical cars, providing the energy needed to power the electric motor and propel the vehicle. Ongoing advancements in battery technology aim to improve energy density, charging speeds, and overall longevity, making electric cars more practical and efficient for everyday use. Let's move on to the electric powertrain. The electric powertrain in an electric car consists of the electric motor, the battery pack, and the motor controller. Here is a detailed explanation of how these components work together. First is the electric motor. It is mentioned earlier. The electric motor is responsible for converting electrical energy into mechanical energy to propel the vehicle. When the driver presses the accelerator pedal, it sends a signal to the motor controller indicating the desired level of acceleration or power. The second is the battery pack. The battery pack acts as the energy source for the electric motor. It stores the electrical energy required to power the motor and propel the vehicle. The battery pack is made up of multiple battery cells, typically lithium-ion batteries, which provide a high energy density and can be recharged multiple times. Motor controller serves as the intermediary between the battery pack and the electric motor. It receives the driver's input through the accelerator pedal and adjusts the power flow from the battery to the motor accordingly. When the driver presses the accelerator pedal, a signal is sent to the motor controller. The motor controller analyzes this input and determines the appropriate amount of electrical energy to be supplied to the electrical motor. It regulates the power flow from the battery pack by adjusting the current and voltage to the motor. The motor controller adjusts the current and voltage supplied to the electrical motor based on the driver's input. By manipulating these parameters, the controller can control the speed and torque output of the motor. This allows for precise control over the vehicle's acceleration and performance. The motor controller also plays a crucial role in optimizing efficiency of the electric powertrain. It monitors various parameters such as the state of charge of the battery pack, temperature, and motor performance to ensure optimal power delivery and energy usage. By efficiently managing the power flow, the controller maximizes the range and performance of the electric car. In addition to controlling power delivery, the motor controller also manages regenerative braking. When the driver releases the accelerator pedal or applies the brakes, the motor operates in reverse mode and acts as a generator. The motor controller captures the kinetic energy of the vehicle's motion and converts it back into electrical energy, which is then fed back into the battery pack for storage and later use. This regenerative braking system helps improve overall energy efficiency and increases the range of the vehicle. By integrating the electric motor, battery pack, and motor controller, the electric powertrain in an electric car provides a seamless and efficient way to convert electrical energy into mechanical energy. The motor controller ensures precise control over power delivery, optimizing performance and efficiency while offering a smooth driving experience. Regenerative braking is a feature in electric cars that allows them to recover and recapture energy during deceleration or braking. Here is a detailed explanation of how regenerative braking works. In a conventional car with an internal combustion engine, braking involves using friction to slow down the vehicle. When the brakes are applied, mechanical brake pads press against the wheels of the vehicle, converting the kinetic energy of the moving car into heat energy, which is then dissipated into the environment. In contrast, regenerative braking in electric cars take advantage of the electric motor's ability to operate in reverse mode and acts as a generator. Instead of relying solely on friction to slow down the vehicle, regenerative braking harnesses the kinetic energy of the moving car to generate electrical energy. When the driver releases the accelerator pedal or applies the brakes in an electric car, the motor controller detects this change in input. It then instructs the electric motor to operate in reverse mode. In this mode, the motor functions as a generator, converting the mechanical energy of the moving vehicle back into electrical energy. The vehicle slows down, the wheels drive the electric motor, causing it to rotate. The rotating motor generates a magnetic field that induces a current in the motor windings. This current is then converted into electrical energy. which is fed back into the battery pack for storage. By converting the kinetic energy of the vehicle into electrical energy, regenerative braking allows electric cars to recover and store energy that would otherwise be lost as heat in conventional braking systems. This recovered energy increases the charge level of the battery pack, effectively extending the vehicle's range. The amount of energy that can be recovered through regenerative braking depends on various factors, including the vehicle's speed, weight, and the force applied during braking. In some situations, regenerative braking can recover a significant portion of the energy, particularly during moderate braking or when traveling downhill. While regenerative braking is effective in most situations, there may be times when additional braking force is required, such as during sudden or emergency stops. In such cases, electric cars also utilize traditional friction-based mechanical braking systems, similar to those found in conventional vehicles, to provide the necessary stopping power. The electric car's braking system seamlessly integrates both regenerative braking and mechanical braking for optimal braking performance, maximizing energy recovery. By employing regenerative braking, electric cars can enhance their overall energy efficiency and range. The recaptured energy during the acceleration and braking is used to recharge the battery pack, reducing the reliance on external charging sources and increasing the car's driving range. This feature contributes to the sustainability and eco-friendliness of electric vehicles. Let's move on to the charging of electric vehicles. As mentioned above, level 1 charging is the slowest method of charging an electric car and is done using a standard household outlet. It typically requires a 120-volt power source. Level 1 chargers come with most electric cars and use a portable charging cord that plugs into a regular wall socket. Due to the lower voltage and current, Level 1 charging is relatively slow, typically providing a charging rate of around 2 to 5 miles of range per hour of charging. It is convenient for overnight charging at home or when there are limited charging options available. However, it may not be sufficient for quickly replenishing the battery life if the car has a large capacity or if there is need for frequent long-distance travel. Level 2 charging is a faster method that requires a dedicated charging system. These charging stations provide a higher charging rate compared to level 1 charging. Level 2 chargers use a 240 volt power source, similar to what is used for large home appliances like electric stoves or dryers. Level 2 charging stations can fully charge an electric car in a few hours, depending on the vehicle's battery capacity. The exact charging time varies based on factors such as the vehicle onboard charger capacity and the available power at the charging station. Level 2 chargers are commonly found in public charging stations, workplaces, and some residential garages. Direct current fast charging, also known as level 3 charging, is the fastest charging option available for electric cars. It offers significantly higher charging rates compared to level 1 and level 2 charging. DC fast chargers apply a high-powered direct current directly to the vehicle's battery by passing the onboard charger. Direct current fast chargers are typically found at public charging stations along highways, commercial areas, and some few residential areas. They can charge an electric car to 80% or more of its battery capacity in around 30 minutes, depending on the charging infrastructure and the capabilities of the vehicle. However, it is important to note that the charging speed may vary depending on the specific vehicle's charging capabilities and the power output of the charging station. It is worth mentioning that not all electric cars support direct current fast charging. The vehicle must be equipped with the necessary charging hardware and be compatible with the charging infrastructure. In summary, electric cars can be charged through different methods depending on the available charging infrastructure and the desired charging time. Level 1 charging is convenient for overnight charging at home. Level 2 charging offers faster charging at dedicated charging stations, and direct current fast charging provides rapid charging for longer trips or when a quick charge is needed. The choice of charging method depends on individual needs, travel requirements, and the availability of charging infrastructure. The range of an electric car refers to the distance it can travel on a single charge of its battery pack. Early electric cars had limited ranges, primarily due to their lower energy density and capacity of the available battery technology at the time. However, advancements in battery technology have significantly improved the range of modern electric cars. Modern electric cars can achieve ranges of over 200 to 300 miles or more on a full charge, depending on various factors such as battery capacity. The capacity of the battery pack plays a significant role in determining the range of an electric car. However, higher capacity battery packs can store more electrical energy, enabling longer ranges. The efficiency of the electric drivetrain, which includes the electric motor and the power electronics, affects the overall range. More efficient drivetrains can convert a higher percentage of energy from the battery into actual vehicle movement, reducing energy waste and extending the range. The range of an electric car can vary depending on driving conditions such as speed, terrain, temperature, and use of accessories like air conditioning or heating. Higher speeds, hilly terrain, extreme temperatures, and increased accessory usage can impact the range by consuming more electrical energy. Aggressive driving habits such as rapid acceleration or frequent hard braking can reduce the range of an electric car. Smooth and efficient driving techniques, including gradual acceleration and anticipation of traffic flow, can help optimize the range. Electric cars are generally more energy efficient compared to internal combustion engines vehicles. This higher efficiency is due to several key factors. Electric motors are highly efficient at converting electrical energy into mechanical energy and achieve efficiencies of over 90%, meaning they waste relatively little energy in the conversion process. As mentioned earlier, electric cars employ regenerative braking, which allows them to recover and recapture energy during the acceleration and braking. This energy recovery system reduces energy waste and increases overall efficiency. Electric cars do not have the same energy losses associated with the combustion process found in internal combustion engines. They don't produce waste heat, and their drivetrains operate more efficiently, resulting in lower energy waste. Electric cars are often purpose-built or redesigned from the ground up to be electric vehicles. This allows for design optimization that maximize energy efficiency, such as aerodynamics design, lightweight materials, and improved thermal management systems. Overall, the combination of a higher energy conversion efficiency of electric motors and the ability to recover energy through regenerative braking makes electrical cars more efficient compared to internal combustion engine vehicles. This efficiency contributes to their longer driving ranges on a single charge and their reduced environmental impact. It is also important to note that the range and efficiency of electric cars can vary depending on the specific model, battery capacity, driving conditions, and individual driving habits. Advancements in battery technology and ongoing research and development efforts continue to improve the range and efficiency of electric cars, making them increasingly practical and more viable for everyday use. As the popularity of electric cars increases, the charging infrastructure is expanding to meet the growing demand. Public charging stations are being installed in various locations to provide convenient access to charging for electric car owners. These stations are typically found in shopping centers, parking lots, office complexes, and along highways. Public charging stations come in different types, such as level 2 chargers and direct current fast chargers, offering various charging speeds. Level 2 chargers, with their higher charging rates compared to level 1 charging, are commonly installed in public charging stations. They can fully charge an electric car in few hours, making them suitable for longer stops, such as during shopping or dining. DC fast chargers are strategically located along highways and in areas with high traffic volume to provide rapid charging. These chargers supply a high-power direct current to the vehicle, allowing for quick charging times, typically around 30 minutes, to charge an electric car to 80% or more. Public charging stations often offer additional amenities, such as parking spaces reserved for electric vehicles, dedicated electric vehicle charging apps for payment, and located nearby stations, and sometimes even charging services provided free of charge or at a normal fee. Many electric car owners choose to install charging stations at their home for convenient and reliable overnight charging. Residential charging stations, also known as home chargers or level 2 chargers, are typically installed in garages, carports, or driveways. Home charging offers a faster charging rate compared to level 1 charging using a standard household outlet. They use a 240-volt power source. This allows for quicker charging times, typically ranging from a few hours to overnight, depending on the battery capacity and the charging rate of the vehicle. Residential charging stations provide electric car owners with the convenience of having a dedicated charging point at home, ensuring that their vehicle is ready to go each morning. They also offer the flexibility to charge the car at any time, taking advantage of lower electric rates during off-peak hours. Workplace charging stations are becoming increasingly common as employers recognize the benefits of supporting electric car adoption among their employees. These charging stations are typically installed in office parking lots or designated parking areas. Workplace charging stations allow employees to charge their electric cars while they work, providing an additional charging option for those who may not have access to residential charging. This not only helps employees with their daily charging needs, but also encourages the use of electric vehicles by alleviating range anxiety and providing a convenient charging solution during the workday. To facilitate access to charging stations, charging networks and mobile apps have been developed. These networks and apps provide information about the location, availability, and status of charging stations, allowing electric car owners to plan their routes and find charging stations easily. Some charging networks offer membership plans that provide access to a network of charging stations and streamlined payment processes. These charging networks and apps helps create a seamless charging experience by integrating various charging stations under one platform, making it more convenient for electric car owners to locate, use, and pay for charging services. In summary, The charging infrastructure for electric cars is expanding rapidly to meet the growing demand. Public charging stations are being installed in various locations, offering different charging needs and amenities. Many electric car owners also choose to install home charging stations for convenient overnight charging. Workplaces charging stations further support the adoption of electric vehicles. Charging networks and mobile apps simplify the process of locating and accessing charging stations, creating a more seamless charging experience. Battery technology is a critical factor in the advancement and success of electric cars. Over the years, there have been significant developments in battery technology, particularly with the use of lithium-ion batteries, which have greatly enhanced the performance and practicality of electric vehicles. Energy density refers to the amount of energy that can be stored in a given volume or weight of a battery. Higher energy density means that a battery can store more electrical energy, allowing for increased range in electric cars. Advances in lithium-ion battery technology have led to substantial improvements in the energy density. Lithium-ion batteries offer higher energy densities compared to previous battery technologies, such as nickel metal hydride or lead-acid batteries. These improvements in energy density has enabled electric cars to achieve longer ranges on a single charge, making them more practical for everyday use and reducing range anxiety among drivers. Battery longevity, or the lifespan of a battery, is an essential aspect of electric cars ownership. The ability to retain a high capacity over an extended period is crucial for the long-term usability and value of electric cars. Advancements in lithium-ion battery technology led to improvements in battery longevity. Manufacturers have developed battery chemistries and cell designs that are more resistant to degradation, allowing the batteries to maintain the capacity for a more extended period. Battery management systems, which regulate the charging and discharging process, have also played a vital role in prolonging battery life. Faster charging times are crucial for the practicality and convenience of electric cars. The development of battery technology has facilitated faster charging capabilities, reducing the time required to recharge electric car batteries. Improved lithium-ion battery designs and chemistries, combined with the advancement in charging infrastructure, have enabled faster charging rates. DC fast charging, for instance, can rapidly charge an electric car up to 80% or more in around 30 minutes, depending on the specific charging infrastructure and the capability of the vehicle. Technology continues to evolve through ongoing research and development efforts. Researchers and scientists are exploring new materials, chemistries, and designs to further enhance their performance, energy density, longevity, and safety of batteries. Some promising areas of research include solid-state batteries, which use solid electrolytes instead of liquid electrolytes, offering potential advantages in terms of safety, energy density, and faster charging. Other areas of exploration include new electrode materials and designs, such as silicon-based anodes, which can improve energy storage capacity. Investment in research and development, both from automotive manufacturers and the wider scientific community, aims to address the remaining challenges and push the boundaries of battery technology. This ongoing progress will continue to drive improvements in the efficiency, range, and overall practicality of electric cars. In summary, advances in battery technology, particularly with lithium-ion batteries, have led to a transformative impact on electric cars. Higher energy density, improved battery longevity, and faster charging capabilities have made electric vehicles more efficient, practical, and appealing to a broader range of consumers. Ongoing research and development efforts in battery technology aim to further enhance these aspects, paving the way for a sustainable and electrified future of transportation. Let me put some electric car manufacturers and their contribution to the electric vehicle market. Tesla. Tesla is a pioneer in electric vehicles manufacturing system and has played a significant role in popularizing electric cars. They offer a range of electric models, including the Model S, Model 3, Model X, and Model Y. Tesla's vehicles are known for their long-range capabilities, innovative technology, and high performance features. They also have a developed supercharger network providing fast charging options for Tesla owners. And Nissan introduced the Nissan Leaf, one of the world's best-selling electric cars. The Leaf offers a practical and affordable option for everyday driving with a range suitable for urban and suburban environments. Nissan has been actively involved in advancing electric vehicle technology and promoting sustainable mobility. Chevrolet offers the Chevrolet Bolt electric vehicle, an all-electric vehicle compact car with a competitive range and affordable price. The Bolt electric vehicle has gained popularity for its practicality and versatile design, making it a popular choice for those seeking an electric vehicle for daily commuting. BMW has made significant strides in the electric vehicle market with its BMW i-Series, which includes models such as the BMW i3 and BMW i8. The BMW i3 is a compact electric car known for its distinctive design, efficient performance, and use of sustainable materials in its construction. Audi has entered the electric vehicle market with models like the Audi e-tron and the Audi e-tron GT. These vehicles combine Audi's renowned luxury and performance with electric powertrains, offering a premium electric driving experience. Hyundai and Kia have made notable advancements in electric vehicles. The Hyundai Kona electric and Kia Niro electric vehicle are popular electric SUVs with decent range capabilities and practicalities. Hyundai and Kia have demonstrated their commitment to electric mobility, with plans for further electric vehicles development and expansion. Jaguar introduced the Jaguar I-Pace, an all-electric luxury SUV. The I-Pace combines elegant design, advanced technology, and impressive performance, positioning Jaguar as a key player in the luxury electric vehicle market. These are just a few examples of the many electric car manufacturers in the market. As the demand for electric vehicles continue to grow, both the traditional automakers and new entrants are investing in electric vehicle development, contributing to a more diverse and competitive electric car market. Now let's talk about the future development in electric car technology. The first one is the improved battery technology, where researchers and manufacturers are focused on developing batteries with higher energy densities, allowing for longer driving ranges on a single charge. Advancements in battery chemistry and materials, such as solid-state batteries or lithium-ion batteries, have the potential to significantly improve the range of electric cars. Expansion of fast charging infrastructure is a key focus for the future. Efforts are underway to develop ultra-fast charging stations that can deliver high-power charging capabilities, reducing charging times even further. This will enhance the convenience and practicality of electric cars, and as a result, making long-distance travel more feasible. The wireless charging technology, also known as inductive charging, is being explored as a future charging solution for electric vehicles. This technology enables charging without the need for physical cable connections, allowing for more seamless and convenient charging experiences. Research and development efforts are underway to improve the efficiency and practicality of wireless charging systems. Electric vehicles have the potential to serve as mobile energy storage systems. Vehicles to grid technology allows electric car to not only draw electricity from the grid, but also return excess energy back to the grid when needed. This bidirectional flow of energy can help stabilize the grid during peak demand periods or serve as a backup power during emergency. Lightweight materials such as carbon fiber, reinforced polymers, and aluminum alloys can help reduce the weight of electric vehicles. Lighter vehicles require less energy to propel, resulting in improved efficiency and increased range. Additionally, optimizing the design and efficiency of electric motors and power electronics can further enhance the overall performance and energy efficiency of electric cars. Electric cars and autonomous driving technology are often seen as complementary. As autonomous driving technology continues to develop, electric cars can benefit from advanced driver assistance system and self-driving capabilities, making transportation safer, more efficient, and convenient. In addition to passenger cars, there is a growing focus on the electrification of commercial vehicles, such as buses, delivery vans, and trucks. The development of electric commercial vehicles can have a significant impact on reducing emissions in the transportation sector, particularly in urban areas where pollution from diesel-powered vehicles is a concern. These future developments aim to further enhance the performance, range, charging infrastructure, and overall practicality of electric cars. As technology advances and these innovations become more widespread, electric cars are expected to become an even more viable and mainstream transportation option, contributing to a cleaner and more sustainable future. Winding up, electric cars have emerged as a transformative force in the automotive industry, offering numerous advantages and driving the transition towards a more sustainable future. With their zero tailpipe emissions, improved energy efficiency, reduced operating costs, compatibility with the renewable energy sources, noise reduction, and government incentives, electric cars have gained significant popularity and continue to evolve rapidly. The environmental impact of electric cars cannot be overstated. By eliminating the tailpipe emissions, electric vehicles play a crucial role in reducing air pollution and greenhouse gas emissions. With a global focus on combating climate change and improving air quality, electric cars provide a cleaner and greener alternative to conventional vehicles powered by internal combustion engines. They contribute to mitigating the environmental challenges we face and help pave the way for a more sustainable future. As in terms of energy efficiency, electric motors outperform internal combustion engines by converting a higher percentage of energy into actual vehicle movement. This means that less energy is wasted during operation, resulting in reduced energy consumption and lower overall fuel costs. With advancements in battery technology and the expansion of charging infrastructure, electric cars are becoming increasingly practical and convenient for daily use, with longer driving ranges and faster charging capabilities. One of the significant advantages of electric cars is their compatibility with renewable energy sources. As the world transitions to cleaner energy generation, electric cars can be charged using electricity produced from renewable sources such as solar, wind, or hydroelectric power. This synergy between electric vehicles and renewable energy contributes to a more sustainable and decentralized energy ecosystem. The noise reduction offered by electric cars enhances the driving experience and contributes to quieter urban environments. With their silent operation, electric vehicles are well suited for densely populated areas, reducing noise pollution and making them a favorable choice for those seeking a more peaceful and serene driving experience. Government incentives and support programs have played a crucial role in promoting the adoption of electric cars. Financial incentives such as tax credits, rebates, and subsidies have made electric vehicles more accessible and attractive to consumers. The government have also invested in the expansion of charging infrastructure and implemented policies to encourage the development and adoption of electric vehicles. These initiatives are accelerating the transition to a cleaner transportation system and fostering a more sustainable mobility landscape. Looking ahead, the future of electric cars holds tremendous potential. Ongoing research and development efforts aim to further improve battery technology, enhance charging infrastructure, and optimize the overall performance and efficiency of electric vehicles. As these advancements continue, electric cars will become even more practical, affordable, and widely accessible. In conclusion, electric cars represent a significant step towards achieving a sustainable and low-carbon transportation system. Their environmental benefits, energy efficiency, reduced operating costs, noise reduction, and compatibility with renewable energy sources make them an attractive and promising alternative to conventional vehicles. With continued innovation and support from government, electric cars will continue to revolutionize the automotive industry, contributing to a cleaner, greener, and more sustainable future for generations to come. Please subscribe to our channel for more automotive content.